Imagine a tiny solar system. At the center lies the sun, a dense nucleus. Whizzing around it are planets, the electrons. This was the early model of the atom, a delicious-sounding plum pudding where electrons were sprinkled like plums in a positive pudding. But this model had a fatal flaw. See, in the world of classical physics, when an electron circles a nucleus, it's constantly accelerating, and accelerating charges emit energy. Imagine a child on a merry-go-round, constantly losing energy. What happens? The child slows down, drifts inward, and eventually crashes into the center. This is the predicament of the plum pudding atom. Electrons constantly losing energy should spiral into the nucleus. Atoms, the building blocks of everything, should be inherently unstable, prone to collapse. But we see, touch, and breathe a world made of stable matter. So where did classical physics go wrong? The answer lies in the limitations of classical physics itself. It worked perfectly for large objects like apples falling from trees or planets orbiting the sun. But when we entered the microscopic world of atoms, classical physics faltered. It couldn't explain why atoms, with their orbiting electrons, didn't simply disintegrate. The problem wasn't the math, it was the underlying assumptions. Classical physics treated electrons as tiny, solid particles with well-defined positions and speeds. This view, while intuitive for everyday objects, proved utterly inadequate for describing the bizarre reality of the quantum world. Atoms shouldn't exist according to classical physics. Yet, here we are, living proof of its limitations. This discrepancy, this catastrophe as some physicists called it, demanded a radical departure, a complete reimagining of the subatomic realm. And so, quantum mechanics was born. Quantum mechanics, a revolutionary framework for understanding the microscopic world, emerged as the savior of the atom. It introduced a wave-particle duality, suggesting that particles like electrons can also behave like waves. Imagine a pebble dropped in water creating ripples that spread outward. Electrons, too, exhibit this wave-like behavior. But how does this wave nature prevent atomic collapse? Here's where another revolutionary concept comes in: Heisenberg's uncertainty principle. This principle states that we can never know both the position and momentum of a particle like an electron with perfect accuracy. The more precisely we know one, the less we know the other. Imagine trying to pinpoint a flickering candle flame in a dark room. The act of observing it, of shining light on it, inevitably makes it flicker even more. Similarly, trying to precisely measure an electron's position introduces uncertainty in its momentum, and vice versa. Quantum mechanics, with its wave-particle duality and inherent uncertainty, paints a radically different picture of the atom. Electrons aren't tiny planets orbiting a nucleus but rather blurry clouds of probability, their positions smeared out like waves. They exist in specific energy levels, not as particles confined to precise orbits. The uncertainty principle prevents electrons from collapsing into the nucleus. Confining an electron to the tiny volume of the nucleus would require knowing its position with high certainty. This in turn would make its momentum highly uncertain, giving it enough energy to escape the nucleus's pull. Thus, the very act of trying to confine an electron prevents its collapse. Quantum mechanics, with its embrace of uncertainty and wave-particle duality, provides the key to understanding the stability of atoms, the building blocks of our universe. The catastrophe of classical physics becomes a triumph of quantum mechanics, revealing the profound strangeness and elegance of the subatomic world.